And so exciting work here to show. So at this edition of the conference, we decided to organize a seizure detection challenge. This is the first time a seizure detection challenge was organized in the context of this conference. There have been a few others in the past in some machine learning conferences, that ICAST, for example, 2 years ago that some of you might know about, more focused on wearable EEG and small form factors with very low number of electrodes. In this presentation, I'll go over why we organized the challenge, how we did it, and then what we obtained as results. So this challenge was decided by the organizing committee of the conference and was made possible thanks to the support of Ceribell, which kindly offered to sponsor the prize money that will go to the winners. And this is a big effort, so it involves many people. I'm here representing the effort, but it is way more than this. So I'm Jonathan Dan from EPFL, from David Atienza's lab, the Embedded Systems lab. I had a lot of support from 2 colleagues in the lab, Amir Hossein Shabazinia and Christodoulos Kekris. I also had a lot of support from the research computing platform of EPFL. You'll see later in the presentation that this required quite a lot of compute, and also a lot of support from the organizing committee of the conference in publicity, dissemination, and organization of the whole challenge. So let's get straight into why we're organizing it. And we're organizing it because we all are faced with the problem that it is very, very difficult to identify the best seizure detection algorithms around. It is a question that I, working in the field for a few years, I'm unable to tell you today which are the best ones. And I think none of us in the room really know which ones are the best ones. So we don't really know where we are. We do have reviews, and we have reviews coming out every year. I'll show you here a few reviews that have come out recently. But these reviews are flawed, and they're flawed for several reasons. One of the reasons is that they tend to report also reported metrics. And these metrics are computed in many different ways, on different data sets, different mechanisms for splitting the training data, the test and the validation data, different ways of computing performance metric, and so we're just not talking about the same thing. And we even have seen in this conference people presenting results comparing to themselves, which is great, but which doesn't really allow to know where we are compared to others. So this is one study that came out, another study that came out. This one only focuses on accuracy. We kind of know that accuracy as a metric in highly unbalanced data sets is probably not the best metric to use. We have another one from 2021 again, and still another one from 2020. I mean, it's just telling you they come every year in big journals, in smaller journals, and they get cited. I mean, some of these here are cited more than 200 times, even though they're only 2 years old. So there's work to do here. So that's why we decided to organize the challenge. So how do we organize a challenge? Well, we say, okay, we have data, and luckily we have in the organizing committee Sándor Benitsky, and Sándor Benitsky had access to a high-quality data set of people with epilepsy that had been carefully annotated by highly trained neurologists. So we have a data set that no one has ever seen, and we know that many of you around here have algorithms. We still need to find a way of communicating, and communication goes through standardization. So standardization of what is the input data that you will have to work on, and standardization on what is the output that you will have to provide for us to evaluate it. And so that's how we set up a challenge. So around this standardization, and then what we do is we run the inference, so we run the algorithms on the data that you have never seen, you will never have access to it. We can then run the evaluation, compute metrics, and run over all of it on what we call seizure score. And so that's how we organize the challenge. The aim of the challenge is to identify what is the current state of the art in epileptic seizure detection for scalp EEG. That's one of the aims. The other aim of the challenge is to say, well, can we develop a methodology that allows to benchmark seizure detection algorithms? And that goes beyond the context of this specific conference, and where we can continue to build on these findings and to see where are we in 1 year, in 2 years, in 3 years, if we replicate these type of methods. So I've been talking about seizure score. Seizure score is actually something that I presented to you last year. It was work in progress, and we were working on how can we validate seizure detection algorithms. It's gone a long way since I was showing you where we were last year. Thanks to many of you, thanks to feedback, thanks to work of the reviewers in publishing this work, thanks to many people that developed code also. And so it grew into a framework for the validation of seizure detection algorithms. It defines a few things that I'll have to remind to you today in the audience so that you understand how we organize the challenge. It defines how you format data sets such that we speak the same language when you expect data and when you need to produce output. It defines what the machine learning task is that we're evaluating. What does seizure detection even mean? At what level are we operating? And it defines how we compute performance metrics. So let's get straight into it. I'll only talk about the components which are really relevant to this challenge. And the first thing is to define formats. And these are based on existing standards. And in our community, we have a lot of standards which already exist. We have the EDF file format, the European data format, which is used by many of us, which is an open format and which we can openly and easily exchange files with. The EDF format doesn't exactly determine what you have in your recording. How many channels do you have in it? What is the sampling frequency? What is the name of the channels? And this variability could be difficult to handle for algorithms. We also have recommendations from the International League Against Epilepsy on the minimum requirement standards for high-quality EEG recordings. And we also have work that has been done more recently on the brain imaging data structure, on how do you organize data sets and how do you accompany metadata and annotations with the EEG files. So based on all of that, we defined the stricter subset of all these rules, which was to say that in the context of seizure detection for scalp EEG, let's initially work on the problem where we have scalp EEG at 256 hertz with a 1020 electrode, so 19 electrodes, all referenced in a unipolar montage. Let's accompany each one of these files with a TSV file that will contain the annotation. This is a tab-separated value file. And in it, the file will specify the onset and the duration of every event. These events will be marked with a code, and this code must comply with the seizure classification guidelines of the International League and with a vocabulary that is compliant with head score. And all these files will be organized in the bits hierarchy. So on that, we build code. I mean, if we don't have common code, each one needs to re-implement, and it does become difficult to make sure that we respect the standard in a correct way. And so we built libraries that convert the existing public EEG datasets to this bits-compliant format. We call it Epilepsy to bits. We did it on 4 public datasets, and we also did it on the dataset that Sándor Bénicki provided us, such that we're all working with the same format that you could use for training and that we will be using for evaluation. The task in this context is seizure detection on scalp EEG, and we define it as a segmentation task. So in a recording that you will receive, you will have to determine each onset and duration of the seizures in it. So you will have to identify the beginning and end of each seizure. You could imagine other definitions. You could imagine just knowing, is this recording epileptiform or not, or comes from a patient with epilepsy? That would be another task. This is not the task here. The performance metrics that we use are defined in 2 ways to suit 2 communities which sometimes work differently. In the context of this challenge, we will be evaluating algorithms based on the event-based scoring. Event-based scoring is based on overlap. So you have the reference that comes from the clinician, and which marks the beginning and end of a seizure. And then you have the hypothesis, which comes from an algorithm. You consider that as seizure detection if there is overlap between the reference and the hypothesis. And any overlap is enough. Detecting only 1 second out of a 1-minute seizure would be considered as detecting that seizure. In event-based scoring, you need to define a few hyperparameters. The first hyperparameter which we defined is how much overlap is required. In this case, we say any overlap. Another hyperparameter that we define is how much tolerance do we allow. And we consider that if you are 30 seconds before the seizure or 60 seconds after the seizure, we're still talking about the same event. It could be some imprecision in the annotation of the doctor or of the algorithm, and we're still talking about the same thing. We also determined that annotations have got a maximum duration. And we consider that if you give an annotation of more than 5 minutes, it should be split into annotations. This is to make sure that people that would just give one extremely long annotation would not be benefiting from saying, well, I always make 1-hour annotations. I'll probably be right somewhere, and I'll be as good as someone that gives a short one. So this is penalized as being counted as, so one hour would be split into 5-minute annotations. And we also merge very close neighboring events as being the same events. These are hyperparameters, and values are set for them. They're set in discussion with clinicians, and what currently seems to make sense But of course, these are still arbitrary decisions. Still, they're applied on the same way to all algorithms, such that all algorithms are evaluated in the same way. This is one way of doing the scoring. You'll see that in the final reporting on the website, we also do report sample-based scoring. In sample-based scoring, you split your recording into short segments, let's say segments of 1 second, and then you compare for each segment of 1 second, do we agree or not between the reference and the hypothesis. In sample-based scoring, you lose the notion of events, so you lose the notion of how many seizures did I actually detect. You know how many samples of seizures I detected, but not how many events. And so it also becomes very difficult to count how many false positives did I make, how many false alarms did I generate. With event-based scoring or with sample-based scoring, you can then compute true positives, periods that were correctly identified, false negatives, periods that were missed, seizures that were missed, or false positives, events that were marked as being seizures while in reality they were not. These can be used to compute sensitivity, precision, and F1 score, and F1 score is the main metric that we'll be using to compare algorithms. F1 score is the harmonic mean between sensitivity and precision. This means we're putting equal weight on sensitivity and precision, and you'll see in the final table of results, algorithms that do not pay attention to have a high precision, that means that they make comparatively many errors compared to the number of true detections that they make, will be heavily penalized. It's a choice again, and there might be other ways of scoring. Again, code is provided for this through the time scoring library that you can reuse or re-implement the metrics as you want. All of this has been published in Epilepsy for a more detailed description, and all of it is also provided as source code in Epilepsy 2 bits, in the time scoring, which I described, in the seizure score evaluation, which allows to rank to get the performance of a full data set. And you'll see that everything that was used to build the evaluation and the website is also public. Public means that it also engages discussion, and we're very open and willing to contribute on this together. So let's get to the challenge itself. I think you've got enough information on what seizure score is now and how we did that. The challenge itself ran over a period of 2.5 months. It started on the 1st of December, where communication was done and announcements were done to communicate that the challenge was open. Through emails, through mailing lists, through social media. And it attracted quite some visits, at least on the challenge website. So we had more than 7,000 visits to the conference website, quite evenly spread out across the world, with a strong representation of the United States and of Europe and of Southeast Asia, and maybe a weaker one of Africa. That might be a target in future editions, who knows. The submissions closed on the 16th of February, and then the organizers had 2 weeks to evaluate all the submissions. The submissions had to be provided in the form of a Docker container. A Docker container is a program that is packaged in a way that it also defines on which virtual machine it's running. These are systems that allow that if you are running on Windows and I'm running on Linux, and your program needs to run on a specific version of Linux, all of that is defined such that it will run on a virtual machine in the correct Linux version on my computer, and I won't have any issues running it, or hopefully as little as possible. And the data set that we were using is a data set that comes from Dianalund. It comes from the Epilepsy Monitoring Unit. The Epilepsy Monitoring Unit in Dianalund is a bit special in that they use a portable EEG system where patients are free to walk around the building. The data set is a mixture of patients that are coming in for pre-surgical evaluation and that are coming in for epilepsy diagnosis. We have 65 subjects in the data set. About half are male, half are female. Most of them are adults with a median age of 34 years old. The oldest one is 66, and there are a few children in the data set, with the youngest one being 5 years old. In total, we have 4,360 hours of recording. The patients stay a minimum of 1 day and stay up to 1 week, with the median duration being 73 hours, so corresponding to 3 days. During that period of time, 398 seizures were recorded, and that amounts for 8 hours of continuous seizure data. The median number of seizures per patient was 3. All patients had at least 1 seizure in this data set, and the patient with the most seizures had 112. As you see, this is a highly unbalanced data set, and this is a bit in a contrast to some existing data sets like the Temple University EEG seizure corpus, which is more balanced in terms of duration of seizures versus non-seizure. If we compare this to existing public data sets, you see that this is one of the very large data sets. It's the data set with the longest duration, with a high number of seizures and a high number of subjects. which should be a fairly good data set to do an independent evaluation. In total, we received 30 algorithms from 19 different teams. This is way more than we all expected, and we're really thankful to everyone that put work into submitting algorithms. It required quite a bit of compute to evaluate them. This was done on the research computing platform of EPFL. It required 334 GPU hours on A100 machines, which are fairly powerful machines, 97,000 hours of CPU compute, and 392,000 gigabytes of RAM. Luckily that we had a large cluster to run this, but just gives you an idea of the scale to run these things. And to give you an idea, on average, this cost approximately $20 per algorithm to evaluate in university facilities, where we estimate that we're 8 times cheaper than renting on a public cloud such as Amazon or Google Clouds. So here are some of the results that we get. Here I'm showing you the sensitivity, the precision, the F1 score, and the false alarm of the 28 submissions that could be evaluated. 2 could not be evaluated because there were technical errors in the submissions and the corresponding authors never came back to us to correct them. You see that sensitivities range from practically 1 all the way down to 0. So some algorithms are detecting everything, some are not detecting anything. See that false alarms range from 1 per day to more than 200 a day. And precision never reaches more than 40-something%. And as we evaluate on F1 score, which is this harmonic mean between sensitivity and precision, well, with a limited precision, you have a limited F1 score, and the highest F1 scores you're going to obtain are close to 40% also. So we did some analysis. I mean, we didn't have much time, so we didn't do much analysis on the results that we obtained. One thing that we looked at is what is the percentage of algorithms that detected seizures. And you see that the seizure that was the easiest to detect was detected by 26 out of 28% of the algorithms submitted. And you see that one of the seizures was not detected by any algorithm. And this follows a fairly linear trend. What does that mean? What do the algorithms, which one should be included in the study and excluded? That is for further investigation. We can look at the data, and we see that an easy seizure to detect, even though the visualization could be worked on, is a convulsive seizure with very strong movement, with very strong rhythmic movement. It's fairly long. If you zoom into it, which I did, you do see repetitive patterns, and this indeed should be a fairly easy seizure to detect. You see that the one that was missed by all seizures, by all algorithms, is a bit peculiar. It's also peculiar because this is only a 2-minute recording, and there were gaps, large gaps between the other parts of the recording of that patient, which means that when we fed it to models, they only had 2 minutes of data and didn't have much context, and we know that some of the algorithms were using more context. It's also not entirely clear what is happening here, and this could be reviewed on video EEG. This might also be used as a tool to enhance annotations in datasets. Not saying this is not a seizure, just saying this could be used as a tool. We can use this same type of analysis to look at the errors, which were common for many algorithms. And we see that in general, algorithms don't agree on errors. And so 91% of the errors that are made by the algorithms are not done by more than 1/4 of the algorithms. You see that there are some errors that are done by many algorithms. And here's the error that was done by 22 out of 28 of the algorithms. Not entirely clear to me why this is a particularly difficult segment to analyze. Again, would require more investigation and looking at larger segments of data. This is 5 minutes around the event that was marked. This is where it is. So this is what we've done. And what I want to say here is that even though this is a challenge, the idea is to go further, right? I mean, the idea is to say that this should be used as a benchmark and a tool to evolve year over year. And this requires everyone to be involved in the same project. And so that requires that people discuss and comment on the framework and find better ways of improving it, maybe to different needs, maybe to wearable, maybe to intracranial, maybe to other tasks such as forecasting or multimodal. It also requires that we share code and libraries. So I'll be sharing all the code that was done here. I'll also be sharing the code that was done to convert the dataset. I won't be sharing the data itself because we'll keep it as a holdout dataset. But we do need to continue working on tools that we use in common. We'll keep the evaluation platform open for as long as we can. And we do have funding, so we can probably keep it for quite a few years, which means that we will continue to accept submissions of new algorithms, which will continue to benchmark on the platform. We'll try and do that continuously, and so there is a whole setup already done with a GitHub pull request, which triggers some automatic tests, and then some email notifications to us so that we evaluate it on the RCP platform of EPFL before re-uploading the results. And that can be a way to continue benchmarking the state of the art while keeping a private dataset, a holdout dataset. And even though here we do have an amazing dataset, I think that we will only be stronger if we include multicentric datasets and other datasets. And so this is also a call to anyone in the room that has got some dataset that has not yet been shared publicly, which could be used with annotated seizures such that we can build this multicentric dataset of EMU data that can be used to validate algorithms. And so do reach out to us on the website through my email address. And I'll briefly stop here if there are any questions before going to the results themselves.
Just have a question. Did I get it correctly that the timestamps or the durations could vary between what people submitted, right? Some people could have alarms for 5 minutes, others for 1 second or so. That makes it really statistically complicated, right? I mean, so have you also looked like what was the mean duration of time and warning for the winning algorithms versus the ones that were worse? And my second question, because there could be a sweet spot, right, for the particular data that you have with taking into account how long the seizures were and so on. Have you considered to address this to use like a random predictor that actually uses the times and so on, compare it rather to that?
So to answer the first question here, the choice is to say that we're doing event-based detection. So what counts is, have you detected the epileptic event or are you generating an alarm? That your alarm has got a duration of 10 seconds or has got a duration of 1 second or 5 minutes, you generated an alarm, which means that someone needs to review the data. So I don't really care about the duration that you gave. I just care about the fact that you generated an alarm. So for that part, that was a choice. There are other choices possible, but in this context, it's not time in alert that counts. It's just how many alerts did you make and how many seizures did you detect. Indeed, the suggestion of checking what would a random classifier give would be an interesting one. From this type of data, which is so highly unbalanced, which has got so little seizures compared to the true seizures, it would be very difficult to get a good result if you just do random predictions. Even if you do it at a rate, which is the rate of the amount of hours that you have of seizures compared to the full rate. You just have very little chance of hitting the seizures.
Yeah, but nevertheless, I think you could have two equally performing algorithms. One gives like longer predictions and the other one shorter one. They could, depending on your distribution in your data, give very different results in the end. And they're actually measuring the same, right? So this hypothesis you cannot really exclude. That would be my point.
You know, it's a little bit unfair to bring the most passionate seizure detection discussion at the end of the day. But you know, we are a little bit behind schedule. I would encourage everyone to have this discussion for dinner. So I guess we have an announcement, right?
Yeah, let's move on, and we'll discuss later. So first of all, before the winners themselves, we will acknowledge everyone that gave a submission. We've got 55 people that actively contributed to the algorithms here. This is just huge, right? I mean, this is from 19 institutes, 55 people. It's half the people in this room, nearly, maybe a bit less. So they don't fit in one slide. So here's the second slide with the rest of the people. So now let's move to the winners. We'll start with the second place winner. The second place winner is the team of Chambon et al., a team from a private French company called Relieve, Relieve.io. They obtained an F1 score of 36%, sensitivity of 39%, precision of 42%, and 3 false alarms per day. We have some details on the model, even though we don't know everything on it. We know it's a model that takes 10 seconds of input EEG data and bases its classification on that. It is a combination of a CNN backbone with some transformer blocks. I have not seen the precise architecture itself. It's something to be discussed with the authors. And we know that it has been trained on multiple data sets, which is probably part of the winning recipe, on TUH EEG seizure corpus, on PhysioNet CHB-MIT, on PhysioNet Siena, and on a private source of data. And so thanks to Ceribel, they win a prize of 3,000 francs. Well, congratulations to them. It is dollars and not francs, but I mean, anyway. And the first prize goes to the team of Wu et al. From Rensselaer Polytechnic Institute. They obtained an F1 score of 43%, sensitivity of 37%, precision of 45%, and a false alarm rate of 1.34 per day. They also published their source code openly, not the training code, but the architecture itself. So the architecture of the model is known. They claim that they trained it on public datasets, which are currently not specified. It would also be interesting to know on which combination of public datasets they obtained this good result. We know that they used a transformer, a sequence-to-sequence encoder, that has got multiple blocks to get to an encoding before bringing a decoder, which in some way does mean that it does not give a classification on a window basis, but directly transforms a sequence, so directly works in the event space, which might also explain part of the good results that they obtain. It also means that they are not strictly bound to a segment length, but that probably, if I understood the model correctly, this could take variable input lengths and give variable outputs lengths out. Well done to them. So I believe we'll close it here.
I just wanted to say this is a tremendous amount of work from Jonathan's team at EPFL. So, Jonathan, amazing work as a competition master. Thank you very much.